So on Wednesday, we talked about root locus, and basically we're in the process of solving this example, but to give a quick recap of root locus, basically what we do with root locus is we have an open loop transfer function, and in that open loop transfer function, we can adjust the gain k. And when we put this open loop transfer function into closed loop feedback form, adjusting the gain k will change the pole locations, as you can see here. As I increase k, my poles will become uh, complex conjugate poles in this particular example. That's not always the case where you increase k, where it will become complex conjugate poles. Sometimes it might become real repeated poles or real poles. It just depends. And then we talked about phase and magnitude for the we're talking about phasors, and we're talking about polar form of the poles when in zeros when they're in the imaginary plane, and how to find the angle. And now we're in the example of finding the magnitude and phase of this transfer function evaluated at s is equal to -2 plus j, as example of the review. So you won't find, I don't think you'll find this review in chapter 8. You'll probably find it in chapter 10, but I want to go over this now because it overlaps with root locus on the techniques we use to draw the root locus. Anyway, so basically what we did was we factorized the denominator and found that the denominator has a pair of complex conjugate poles and a pole at -4 and a 0 at -3. So we drew that on the pole zero map. And then to evaluate the phase and angle of this transfer function at this point, this green point, -2 plus j, we put that dot on the pole zero map, and basically we just draw a bunch of lines connecting to it. Those lines are magnitude of each pole and each zero. And then what we're going to do is we're going to take the sum of the zeros angle and subtract it by the sum of the pole angles, and that's going to be our phase of our transfer function, which follows this equation above, where the magnitude is going to be basically the two norm of each zero multiplied by each other, divided by the two norm of each pole multiplied by each other, and the phase is zero angles minus the pole angles. So we found the magnitude, and now we're looking for the phase. And this is where I advise you to be really cautious about signs. And there's a way of how I do it, of finding the angles. And you won't make mistakes if you do it this way. It requires you to just write out every step. But basically, for finding angle of G at -2 plus J, so let's just find the angle of the zero. So visually, when you draw out, you can see that our angle psi 1 is going to be equal to the arctan of 1 over 1. But we can see visually that. But to, I guess, do it properly, the way I do it is basically I'm going to put the height. So I'm going to put these values first. So the height is going to be 1 in the numerator, and the length is going to be -2. And then maybe in a different color, we're going to subtract the difference in the height now in the length. Then 1 minus the pole, or the zero here, has a height of 0. And the pole has a length of -3. So -3. So we get 1 over 1. Arctan of 1 over 1. We don't even need a calculator. We can just see that that's 45 degrees. And in my example, I have it in degrees, so we're going to do it in degrees. So that's how I do it. I take the evaluated point, the height and the length of the evaluated point, and I subtract it by the location of the zero or the pole. and we include the negative as well. So here it's -2 minus -3, it becomes 1. Now let's find theta 1. Same thing. I mean, visually, I can just tell that the height is going to be, so it starts at -2 and goes to 1. So it's going to be 3 over 1, but it's 1 to the left, so it's -1. But I'm not going to do that. I'm just going to write out all the steps, guaranteed it'll be okay then. So we start at the height of 1, and then we are at the length of -2 again. And then now we're going to subtract the difference in height. So 1 minus -2. And then in the length, we get -1. So -2 minus -1. And that gets us arctan of 3 over -1. So now this is where we have to consider quadrants, where this can either be this angle here, where the angle is between 90 and 180 degrees, or it's going to be between 270 and 360 degrees, or base. Yeah. So we want to consider the quadrant here. It looks like it's in quadrant 2, the angle. So then we're going to pick an angle that represents quadrant 2, and then the angle is 108.4 degrees, which makes sense. It's between 90 and 180 degrees. Now, if your calculator gives you 108.4 plus 180 degrees, I think that's going to be what? 288.4 degrees. If you're at 288.4 degrees, mathematically they're the same, but I want you to subtract or add 180 degrees to get it to quadrant 2, because this is the angle we're going after. Okay, so then we're going to do the same for theta 2 and theta 3. So I won't write it out this time. So theta 2 is just going to be 1 and then -2. And then it's going to, and then the length is -2 minus -1. I feel like I messed up something. No, I think we're good. I think we're good. So we get arctan of -1 over -1. So it's the same as saying arctan of 1, which is, if you put that in your if you put this in your calculator, you're gonna get 45 degrees, but we're not at 45 degrees, we're actually at 135 degrees. Because this is quadrant 3. This is quadrant 2 angle. This is a quadrant 3 angle, so we want those angles. Okay, so now that we have that, we just find the angle. We just do sum of G is equal to, oh, I'm missing theta 3. So I'm running out of space. I'll just do theta 3 on the right. It's going to be tan inverse of, it's going to be 1 over 2 here. So it's going to be 1 minus 0, and then -2 minus -4, and we get arctan of 1/2. Which is equal to 26.6 degrees. Oh, sorry. This is not 135. It's 45 plus 180, which is 225 degrees. Okay, so then sum of the angles G is equal to psi 1 minus theta 1 plus theta 2 plus theta 3. And we get 45 degrees, roughly. Or actually, I think it's exactly 45 degrees. All right. So that's how you find the angle. And we got the magnitude. This is actually going to come back in chapter 10, but we're also going to use this method right now to basically help refine the sketch for root locus. Any questions? Okay, so we use the root locus to draw the path of the closed loop poles as k is varied, and we want to see if the point S1 is on the root locus path. So what I mean by there is if I were to look at the root locus here, the red is the path, and I want to evaluate some point like here. We know that that closed loop pole falls on this point, but if it's here, it's not on the root locus anymore, meaning it's not feasible for us to reach that location on the pole zero map. It's not possible for the poles to reach that location, like right here. So that's actually what PID controller does. It changes the shape of the root locus such that we can get to this point here now. But for now, all we can do is we can check if that point is on the root locus path. If so this point S1 is on the root locus, this means a closed loop pole exists there, meaning that if we plug in, that means this equation is true. 1 plus kg S1 h of S1 is equal to 0 is valid. That's what it means when we're on the root locus. Or some k. This is true. So maybe I'll write on the side here. If on the root locus, 1 plus kg S1 h S1, if it's not equal to 0, then means that S1 is not on the root locus. So that's what it means. So maybe I'll write it better. S1 is on the root locus. So to find the root locus, so if S1 is on the root locus, then this is true. This is true. So then what that means is that KG, maybe I'll use S1 here just to be specific. KG S1 H S1 has to equal to -1. So that's a true statement. And I'm going to put a 0J right here because there's no imaginary component to it. Then the magnitude of K times G of S1 H of S1 is equal to 1 because we're just taking the magnitude. And that the phase of G of S1, we can ignore the K because it's just a gain. It doesn't affect it. It doesn't affect the angle. The angle of G of H, G H at S1 is going to be equal to the arctan inverse of the imaginary over the real component, which is 0 over -1. Since we're at -1, that means we have an angle of 180 degrees. So this is called our magnitude and angle criterion. That's where they derive it. So a value of x exists on the root locus if it fulfills the magnitude and angle criteria, meaning that kgh has to equal to 1 and that the angle of gh has to equal to 180 degrees or some odd multiple of 180 degrees. Now, another way of redefining the magnitude criterion is another definition is saying that k has to equal to 1 over g of s, h of s. So basically, we can also determine the magnitude required. Let's say we do know that the root locus exists at that point. We can determine what gain k that is for that corresponding root locus, like for that closed loop pole on that particular point. So these are the same. Any questions? And then this z here just means that this like z here just means it's like minus, it's all integers. So it's for all integers. Okay, so we can redefine the magnitude criterion like this, where basically it's just going to be the system gain k is equal to 1 over m. So we just find m as the magnitude of gh. So let m is equal to the magnitude of g of s, h of s. And that's just going to be equal to the product of all the pole lengths divided by the product of all the zero lengths. And the angle criterion is still the same. It's also, if we're doing it in radians, it's going to be 2i plus 1 times pi for radians. So these are our main criterion for checking if a point exists on the root locus, meaning that the closed loop pole is feasible. Okay, so we're gonna move on to actually sketching it now. There will be more complicated sketches. I just want to go over some terminology when you're sketching a root locus. And I'm going to just make a really big plot. It's going to have a bias of having the negative real plane. Have imaginary. We have the real axis. And then let me straighten these two. There we go. Okay. I'm going to draw some random poles and zeros. So I'm going to have a pole right here, a pole right here, and maybe another pole here, another pole here, and then maybe zero here and a 0 here. Okay, so I'm just going to draw a rough sketch of a root locus of this kind of system. And for now, I just have to take my word that this is how it's going to look like. Probably going to look something like that. like that. So root locuses are symmetric about the imaginary axis. So I'm gonna look maybe like that and like that. They share the same entry points here. So these arrows are indicating the travel, like the trajectory of the poles as I increase K. All right. And then, so first thing I'm going to define here is called the real axis intercept. And it's going to be roughly here. It's going to look like that. Basically, it's just going to be the lines in which these arrows converge at. And I'm not doing a great job. Something like that. Maybe a better drawing would be like this, where it's converging to that point. So this is the real, so these are asymptotes. And this is the real axis intercept. I think it's called the asymptote. Real axis intercept. So it's where these asymptotes hit the real axis. This point here is called the breakaway point. It's where the poles depart the real axis. And this here is called the break-in point, and it's where the poles return to the real axis. This here, it's called the imaginary axis crossing. Here we can actually determine, it's called the angle of departure. If we were to draw like a little line here, it's called the angle of departure. And then maybe in blue. So this segment here, this segment here, and this segment here, these are all called real axis segments. So what real axis segments are basically when their trajectory is only on the real axis. So that means there are two poles that exist on this real axis. So like right here, we see a pole in purple. Right here, there's going to be two poles going towards each other on the real axis. They're called real axis segments. And all of these lines, all the trajectory lines, so all of the trajectory lines are called branches. So this is a branch, that's a different branch, this is another branch, that's another branch. So here we have 4 branches. Even though like they share the same real axis segment, we have four branches because there are four closed loop poles in this system. There are four closed loop poles here. And I actually don't think I drew this quite right. I actually think these lines should be going vertically to for this to be correct. I think I need one more pole. I want to say I need one more pole here, and that's going to go this way. I think this is correct now. This is what it's going to look like. And I'll tell you why. So there are five closed loop poles here. So I've done this for multiple years, so I can tell if the root locus is actually drawn correctly or not, just based off of the number of closed loop poles. But I think it's, yeah, I think that's correct now. But this more importantly, I just wanted to find, I wanted to find the terminology. So, so since there are five closed loop poles, there are five branches. There are five branches. And I'll upload these notes today because this is quite a long section. So I'll upload the incomplete notes for this one. Oh, and I guess to be consistent, this is also a real axis segment as well because it's on the real axis. Okay, so all of these things, asymptote, breakaway point, break-in point, imaginary axis crossing, and angle of departure, and real axis intercept are things you can find. So let me move on. So sketching the root locus, basically the first step is to identify the number of branches. So there's one branch per closed loop pole. Root locus is symmetric about the real axis. So this drawing here is symmetric about the real axis. And for real axis segments, for k greater than 0, the root locus exists to the left of an odd number of real axis finite open loop poles and or finite zeros. And we'll go over what that means. Uh, starting and ending points. So the root locus begins at the finite and infinite poles of GH and ends at the finite and infinite zeros of GH. We'll also talk about what infinite poles and zeros mean. But I actually did talk about that briefly in chapter 4 with poles and zeros about, the numerator being infinity is actually also zero. Zeros that make the numerator go to are zeros that make the numerator go to zero includes how do I want to word it? Yeah, so we'll talk about that. Anyway, and then behavior at infinity. So the root locus approaches straight lines as asymptotes as the locus approaches infinity. Okay, so we're gonna start with real axis segments. So what does that mean? The root locus exists to the left of an odd number of real axis finite open loop poles or zeros. And what I mean by that is that we're talking about the real axis segments in blue here. So they're saying there's a way of checking if the root locus exists on the real axis already, and it's by looking at the number of open loop poles, which is in purple here, poles and zeros. So I guess as an example here is if I were to draw this the real axis, imaginary axis, And I'm going to draw a 0 here, a pole at the origin. Doesn't actually matter where it is. Pole here, and maybe a pair of complex conjugate pole, maybe, yeah, pair of conjugate zeros here. Okay, so we're looking at finite open loop poles and zeros. We're talking about, so we want the real locus exists to the left and the odd number of real axis finite open loop poles or zeros. So we're looking at finite. So we can just ignore these. We can ignore the complex conjugate poles and zeros. We can ignore these. I'll explain why. And what we're going to do is we're going to see, does the real locus exist here? Or does it exist here? Or does it exist here? We don't care how it looks like here or there. We don't care about like this. We only care about segments on the real axis. So to do that, we use the angle criteria, where the angle of G of S, H of S is going to be equal to 2I plus 1 multiplied by 180 degrees. And basically, I'm going to call the angle of this 0 here B1, angle of this pole theta 1, angle of this pole theta 2. I'll call this angle theta 3, call this theta 4. I'm going to call this phi 3, and this top one phi 2. Oh, phi 2. Did I use psi? I think I used psi. I'll be consistent. Psi 1, or if you want to use phi, that's fine too. Psi 2, psi 3. Okay. So basically, for this to be valid, basically, psi 1 plus psi 2 plus psi 3 minus theta 1 plus theta 2 plus theta 3 plus theta 4 needs to be equal to a odd multiple of 180 degrees. Odd multiple multiplied onto 180 degrees. Now, if we're evaluating points along the real axis here, the angles of the complex conjugates actually cancel each other out. So only evaluating S on the real axis. Like, I guess for only evaluating S on the real axis. Basically, we can say that psi 2 is equal to minus psi 3. And theta 3 is equal to minus theta 4. Therefore, they cancel each other out because they're symmetric. These complex conjugates are symmetric about the real axis, and we can use that property to our advantage. So then in that case, we only need to evaluate the angles of psi 1 minus theta 1 plus theta 2 is equal to an odd multiple of 2I plus 1 multiplied by 180 degrees. All right. So if I were to take, and let's use, yeah, purple here, this point here. The angle of, if I were to take a point to the right of all three of these poles and zeros. The angle of theta 1 here is going to be equal to 0 degrees, right? Are we following me there? So that's 0 degrees because we're measuring relative to the positive x-axis. And there's no change in angle. Theta 1 is also 0 degrees. And theta 2 is also 0 degrees. So then we do 0 minus 0 is equal to 2i plus 1 multiplied by 180 degrees. Nope, does not work. Fails angle criteria. So the root locus does not exist there. Okay, now if we were to take, maybe I'll do a blue. Yeah. This point, it doesn't matter how much it is to the left of the 0 now. It's just to the left. It can be very slightly to the left. Put it right there. It's still the same. The angles don't change. We now see that psi 1 is equal to 180 degrees. Are we in agreement here? Because now it's to the left. We're now measuring it this way. Theta 1 and theta 2 are still 0 degrees. Now, we plug this into our angle criteria. We get 180 degrees minus 0 is equal to 2i plus 1 multiplied by 180 degrees. This is true for I is equal to 1. So therefore, the root locus exists along this whole line. I'm going to draw it in red. And the one thing about the root locus is that the root locus begins at infinite and finite poles and ends at finite and infinite zeros. That means the root locus starts at my finite open loop pole and ends at my finite open loop 0 here. Okay, now if I were to evaluate, let's do a different color, this point here. All right, well, psi 1 is equal to 180 degrees. Theta 1 is equal to 180 degrees. Theta 2 is equal to 0 degrees. So then we get 180 minus 180 minus 0, which is equal to 0, which is not equal to 2i plus 1 multiplied by 180 degrees. So it fails it. Now, if we were to pick this point here to the left of this pole, you can probably see the pattern now. Psi 1 is equal to theta 1, which is equal to theta 2, which is equal to 180 degrees. We get 180 minus 360 degrees, which is equal to minus 180 degrees, which works because this works for when I is equal to minus 1. Meaning we have a root locus that exists all the way like on the left side of this pole going to negative infinity. Because if we check anywhere along that line, the angle criteria works. So what they mean is the root locus exists to the left of an odd number of real axis finite open loop and poles, open loop poles and or zeros, like to the right. So when I check this point here to my right, I have one 0. If I check this point here, I now have 1 pole and 1 0 there, so it's 2. They cancel each other out, and now I'm back to a even multiple of 180 degrees. When I check here, I have an odd multiple of poles and zeros to my right side on the real axis, meaning that the root locus exists again. So that's what I mean by this statement. And this is a direct statement copied from the book. I don't know how to make it more clear. So maybe it's like if there's an odd number of poles and zeros to your right on the real axis, then the root locus exists at that point. Maybe that's a better way of saying it. Does that make sense? Yeah.
Well, the second one where it's 180 and is at 0. You get 180 equals 2i plus 1 over 80. 0.7 I is equal to 1.
Where? In blue? So where psi is 180 and the zeros are 180 here. Oh yeah. So oh yeah, I see what you mean. Yeah, thank you. Oh, then this should be oh yeah, -1 is still good there. Yeah. All right, so that's how you identify, and we can just ignore any conjugate poles and zeros because they cancel each other out. So with this trick, you can immediately draw the real axis segments on a root locus. You don't need to calculate anything. You can just know that exists. Now, when they're talking about infinite zeros and infinite poles, there's a infinite zero. This root locus, this arrow here is going to an infinite zero all the way to the left, outside of this page, because all root locus starts at an open loop pole and it ends at an open loop zero. And so we're gonna talk about that. What are open loop? What are infinite and finite poles and zeros? So the root locus begins at a finite and infinite poles, open loop poles. So these are open loop poles, and ends at finite and infinite open loop zeros. So let's look at this expression again. And I think on the earlier page, basically I derived it as K divided by NG, or K multiplied by NG dg. And actually, I just realized, sorry, I may backtrack a few pages. Um, the other day I wrote that, oh, missed it. There's no H here. So this is correct. That statement is true. So just to backtrack. Quick apology there. So I need to go back and correct the slide. So I'll correct that slide there. So we get this K multiplied by NG dg divided by 1 plus K times NG NH divided by dg dh. And we get K NG dh divided by dg dh plus K NG NH. So we get this term here. And basically what I'm trying to show is that the root locus starts at the poles. So when we look at K is very small, 0 plus meaning it's basically 0, but it's still finite. Then our transfer function T of S is going to be roughly equal to KNGDH divided by DGDH plus this epsilon value here, where, so let me call this epsilon here, where DGDH is roughly equal to DGDH plus epsilon. Where epsilon is small. Therefore, T of S is roughly equal to KNGNH divided by DGDH. And that's actually this is the open loop poles. So poles of T of S is equal to the poles of G of S, H of S. That's the open loop poles. So we start the root locus at 0, meaning that the root locus starts at the open loop poles. Are we good here? So now if I increase k to infinity, so as k goes to infinity, K, N, G, and H becomes much larger than DG, DH. Therefore, T of S is roughly equal to K, NG, and NG, DH divided by, basically this is overshadowed, K, NG, and H overwhelms DG, DH. So we get K, NG, and H. K's cancel out, which becomes NG, DH divided by NG, and H, which means that the poles of T of S is equal to the zeros of G of S, H of S, and open loop zeros specifically. So this is like a very, very important, this is like a very important relationship on why your root locus starts at open loop poles and ends at open loop zeros. So this is going to be open loop, or this is the closed loop poles of T of S, right? So T of S, there's our closed loop system. So the poles here are closed loop poles. So then we'll just call it today because I need more time on infinite poles and zeros, but we'll continue this on Monday. Any questions? Yeah. The, NG times, oh yeah, yeah, thank you. Thank you. I don't really care about the zeros for the open, like the closed loop zeros, but yeah, this was the correct one. I mean, I do care about the closed loop zeros, but it's not as important for drawing the root locus. It doesn't tell us anything for the drawing the root locus. All right, and we'll continue this on Monday. Yeah. 1 plus KGH. Yeah, yeah. So it is 1 plus KGH, but then what I did was I multiplied DGDH, so then that replaces the 1 there. Yeah. Are you talking about?
No, I was just like you go like one all the way to the left, just doesn't have the K in the bottom.
Oh, yeah, yeah, I see what you mean.
But it should.
Well, yeah, if I were to write this out, let's write it out just to be safe. So it should be KNGDH divided by, so you're talking about here, right? It should be D, G, D, H plus K, N, G, N, H. Yeah.
No, I mean the equation like before that. The one that, not even the one.
Oh,
that-
shoot. Shit. Oh,
Yeah,
my
no,
bad.
Sorry.
Yeah, no. That's good. Yeah, let's fix that. K, G, H. Yeah. All right, yeah, I'm gonna correct that as well. Two corrections to do on these slides. All right, well, thank you